Today, we're really happy to have Heather DeShon. Heather received her PhD from UC Santa Cruz, working on seismogenic zone structure, Middle America Trench in Costa Rica. After receiving her PhD, she was assistant professor at the University of Memphis and is now a professor at Southern Methodist University, SMU. Heather's research areas are earthquake physics, focusing mostly on subduction zones and intraplate faults and seismicity. She works on seismic tomography and seismicity imaging, volcanoseismology and induced seismology. And in the past 2 years, Heather's published on the rupture complexity of the Ecuadorian megathrust, utilizing INSAR and teleseismic observations. The really interesting and very complex event in the oceanic lithosphere just west of the Sumatra megathrust, the moment magnitude 8.6 Wharton Basin intraplate event. Surface deformation and source model for the semi-sopachinoid volcano, again using INSAR and seismic observations. It's a very interesting paper. If you haven't looked at it, the seismicity distributions is very nicely imaging a conduit to the surface of the volcano. And most of the work that she's, quite a few papers in the last few years, most of the work is on topics pertaining to induced seismicity of North Texas, including spectral analysis, stress drop estimation, structural characterization of active faults, fault slip potential of induced earthquakes, and hazards related to induced seismicity. And that's what she'll be talking with us today about, insights and conundrums stemming from the induced earthquakes in Texas. You have.
Well, thank you for inviting me. I'm excited to be here. All of those years in Santa Cruz, and I actually never came to Berkeley seismic labs, so it was good that I could visit in person. So yes, I am going to talk about work that myself and many faculty members at SMU in Dallas have been doing over the last 10, or some of them more years, on a series of earthquakes in the Fort Worth Basin. So because I am in California and I don't expect everyone is also familiar with the oil and gas basins in Texas, I'm going to situate you. So Dallas is located in north central Texas, and Dallas, Fort Worth, and the Denton area, it's about 7 million people, and it's essentially on top of the Fort Worth Basin, which is the Barnett shale gas play. So this is the first shale gas play where horizontal drilling was tied with hydrofracking to produce natural gas out of tight shale, and also where it became necessary to do deeper injection of the waste disposal water. Now, there are other major important oil and gas plays in Texas, including down here in the Eagle Ford, but of course, most famously out in West Texas in the Permian Basin. All right, so I'm not actually going to talk a lot about the Permian Basin today. It has the Delaware subbasin and the Midland subbasin in it, but we're going to think about what the oil and gas induced earthquakes in the Fort Worth Basin, what we've learned from them, and think about what sort of mitigation strategies might be operable in other oil and gas operations out in West Texas. So this again is work. Today I'm going to be
Are you
showing.
still on the first slide?
Yeah.
Okay, I'm sorry, because it looks like the computer might have hung.
No, that was just me being slow.
Somebody wants to come in.
I don't know why. I
What?
admitted Howard, but he's. Sorry, I'm.
You okay? All right. So again, I'm going to focus today on the Fort Worth Basin, and we're going to look at the way I have this organized is what 5 lessons we've learned from the Fort Worth Basin induced earthquakes. And then I'm going to present 5 conundrums that we can't answer with the data set in the Fort Worth Basin. And I'll explain why the Fort Worth Basin data set is, and the SMU catalog is not appropriate as we go along. And then this snapshot is just a snapshot of seismicity in Texas over the last 60 days. I updated it, I think on the airplane on the way here. So it is, should be fairly recent. And you'll see that in fact, it's earthquakes in the Permian Basin out in West Texas that are really dominating the catalog. I am happy to say that the SMU seismic network has not recorded an earthquake in weeks, right? There shouldn't have been earthquakes underneath the major metropolitan area in Texas. And, you know, it's actually good that my undergraduate researchers don't have anything to do. So you have to think about it, the positive. We have no earthquakes.
Just waiting for Thanksgiving.
Oh, it's funny that you should say that. Yeah, so earthquakes in the Fort Worth Basin are primarily induced by wastewater disposal. We haven't had any earthquakes that can be directly tied to hydrofracking. It's actually a fairly clean system in that sense. Also, the seismicity that we've had has been really centered on individual faults, which puts us in a slightly different place than Oklahoma, because Oklahoma had so much seismicity across so many faults, it was almost hard to keep track of. Whereas in the Fort Worth Basin, we really have an opportunity to study seismicity over time on individual faults that were first activated by waste fluid injection. So there were no known earthquakes in this region prior to 2008. It's all associated, all the earthquakes are spatially and temporally associated with the shale gas play. And the maximum magnitude we had was a magnitude 4, and this happened back in 2015. So again, it's 7 million people on top of these earthquakes. And so it's really for the best that the largest earthquake we had was a magnitude 4 versus the mid-magnitude 5s that were seen in Oklahoma. This image is just showing cumulative injection volume. It's just a spatially smooth injection volume. That swirly symbol is actually the injection well symbol officially in any GIS system. And then the earthquakes shown here are actually from the USGS and the SMU catalog. And then the inset is just showing that peak injection in this area actually occurred in 2012, whereas peak seismicity rates by monthly earthquake count occurred after that. But we're going to dive into this figure in much more detail, essentially. So don't worry if it looks a little hard to read right now. All right, so the next thing I'm going to do is show you the geology, because I am a firm believer that you can't understand the earthquakes without understanding the geology. So we're looking at a cross section that basically goes from just north of Fort Worth across into Dallas. So Fort Worth is in Tarrant County. These are two of our more well-known earthquake sequences. This is the Azle Reno earthquake sequence that began in 2014 or 2013. And then this is the Irving Dallas earthquake sequence. And we'll talk about when it began, but it generated felt earthquakes in the mid-magnitude 3 range in early 2015. So what I'm showing here is, again, the basic geology. The pink is just the Proterozoic crystalline basement. The blue is our Ordovician dolomitic limestone unit. It's heavily karsted in some areas, not so much in others. It's about 1 kilometer thick, and this serves as the primary disposal unit for the wastewater that we're interested in this talk. And then this very narrow orange color that is almost impossible to see on this figure is actually the Barnett Shale. All right, so in some places, as at the deeper levels of the basin near the city of Dallas, there is an intervening unit called the Viola Simpson that separates the Barnett from the Ellenberger. And we'll look at these faults in more detail. But the faults associated with the seismicity in this area are all deep-seated in the crystalline basement. They extend up through the Ellenberger and connect directly into the Barnett and go a little bit higher than that, but they do not reach the surface.
May I ask how the geology was determined?
So this is an active oil and gas basin. So there is a lot of wells, and I'm going to show a figure here in a second.
Another question. So these faults, maybe you're going to talk about this, in which case just obviously we can talk about it later. What's I mean, obviously on these faults, I don't know how many faults you're showing there, 10 faults.
Mhm.
Obviously, 2 of them have a set of earthquakes associated with them. Are there any other physical differences between these faults other than?
Richard has found a conundrum. Not only will I talk about it, but of my 5 conundrums, this is one of the conundrums. I'm going to show you some active source data.
Great.
It's really Beatrice's work, but we'll look at it. All right, so you have earthquakes in an oil and gas basin. What are you going to do? You're going to monitor the earthquakes. You're going to locate the earthquakes. In order to understand physical mechanism, you are going to need to know a lot of geophysics, geology, and geomechanics, right? So, it takes a while to gather all of that data. So down at the University of Texas, so anything in orange at the top kind of represents the fact that this is my collaborators down at the University of Texas, because that's their colors. They have spent a lot of time creating a fundamental 3-dimensional basin architecture data set in Petrel and various other software. What you're looking at here, all of those little dots are not earthquakes. These are well data that have been reported to the regulatory agency and can be used with the logs that get reported, right, to kind of back out the 3-dimensional structure of the basin. So I showed a cartoon 2D cross section, but there's really an underlying 3-dimensional data set now. I'm just showing some slices. Here's the top of the ordovician, so that's the top of our injection unit. There's the base of the ordovician. There's an extraction of pore volume. The thing to keep in mind is that the whole basin is essentially dipping, and this corner is Dallas County. All right, so Dallas County is essentially at the down dip of the basin. All right, so that will come into play later. The earthquakes are occurring on faults. It was pretty clear from Oklahoma and Texas that those faults are not new faults, right? They were already there. So where are they, right? You have to try to create a fault database. It's pretty hard, all right? The oil and gas companies in some areas have 3D volumes that they've spent a lot of money collecting. Some companies will release the fault interpretation. Some companies won't. In Texas, it's not required. So Oklahoma required it to some level, but Texas never did. So on the right is a nice framework fault map for the Fort Worth Basin. Austin would be down here where these rock units actually come up to the surface. And then again, here's Dallas County. So SMU would be located right about there. But you always, when you look at the fault map, you always have to keep in mind that it itself is spatially sampled unevenly. Okay, so, you know, in some areas, the faults are actually extracted from that 3-dimensional basin architecture model where the well bore data has shown, or the logging data has shown offset. Some data, there's seismic reflection data, right? So it's the best we have, but you always have to keep in mind that it itself has changing resolution. All right, so what do we do at SMU in my lab? I do high resolution earthquake location and tomography. So when the earthquakes in the Azle area started in 2013, the USGS asked if we had some personnel that could go out and put out some strong motion stations. And we did that, but we also decided to put out some of our own stations that we had in the basement from testing and various things. And so began kind of the more recent North Texas earthquake catalog. So that's the NTX ES network and earthquake catalog. It combines some early work in 2008 and 2009 by Brian Stump, And then SMU did not operate stations for a good amount of time. And then since 2013, we built up stations as felt earthquakes occurred. So it was kind of whack-a-mole. Then our catalog is great, but it never includes the first largest earthquakes. Large being 3.5s, right? It's always the later earthquakes that we capture. At one point, we were operating up to 40 stations. Eventually, the state of Texas stepped in and created the Texas Seismic Network, and they have a mandate that's statewide. And so now SMU works with TexNet, and we continue to operate tiny networks embedded within TexNet, where SMU concentrates on individual faults or areas such as Dallas with higher risk. All right, so the stations over time are on the right. Not all of those stations were out at the same time, right? Some of those stations are literally the same equipment that was moved around. So there's a huge amount of spatial and temporal variability in the SMU earthquake catalog as a result of how we had to operate during this time of increasing seismicity, starting from 2013 and moving into 2016.
Are the SMU stations all like temporary deployments that plug into?
Yeah, they are all under, it's actually all, it's mostly Pascal instrumentation, and it's all considered temporary research networks. We actually operate.
And do they plug into I guess the broader network? And
yeah, so
that's cool.
Because we were monitoring induced earthquakes, and because 3 of the SMU faculty members were tied to IRIS, we telemetered our data real time from the moment we put a station in the ground, and let anyone use the data as soon as we collected it. We never kept any of it proprietary. We didn't have enough people to analyze it, so it's better just to make it publicly available. And then when TexNet became operational, we also had some back channel say in what should be in that original legislation, and requiring TexNet to make all their data publicly available upon collection. That's one of the pieces we stressed to our local representatives. All right, so there's TexNet now. It's statewide seismic network. The first stations went into the ground in 2017. These numbers are out of date, but at the time, it was mandated to go down to magnitude 1.5 across the state. And it was 25 permanent broadband seismometers and 33 portable systems. People, oil and gas companies, various people have been giving TexNet stations to improve their coverage in the Delaware and Midland Basin in particular. And so TexNet's operation has now grown well beyond that. But SMU is just a temporary network that anybody, USGS or TexNet, can use. All right. So Luis Quinones, my PhD student that just recently finished, he made this nice movie. I have already gone a little bit over my scheduled time, but this is just showing you 3 of the earthquake catalogs available for the Fort Worth Basin. So to place you, here's Dallas, Fort Worth is to the west, Denton is pretty good size and to the north. The circle sizes are very big in this particular case. The blue colors represent the SMU catalog. You can see when SMU starts putting stations in with the white triangle or white squares. The green is the USGS, which was always available. And then when the transportable array went through for 2 years, there's also a mini earthquake catalog for that time. So you can see when SMU operates stations, the magnitude of sensitivity goes way down. USGS kind of just hovers up here in the greens at above magnitude 2. And then you can see when we really start putting more stations into the ground back in 2013. We're going to just look at this in some other ways in the next few slides, so I won't stay on it. Here's just the blow up again, Dallas, Fort Worth. There are 5 named sequences, and this is where people get a little confused. The 5 named sequences are named because SMU has published papers about those 5 sequences. It doesn't mean there's actually only 5 active faults in the Fort Worth Basin. That just means there are 5 faults that SMU put seismometers on top of and then created a publication. And so therefore the sequence has a name. The ones that we have best control over are ASL from 2013. What you're looking at here is just a cross section perpendicular to fault strike. In this case, most of the earthquakes are in the basement. So the solid black line represents the top of the crystalline basement. The dotted line represents the top of the injection unit. We have ASL outside of Fort Worth, the Irving Dallas sequence here, and then the Venus sequence, which is in this northeastern corner of Johnson County. Now you'll notice that the dots don't have uncertainty bars associated with them, but most of the earthquakes are in the basement, except in the case of ASL, where it does look like there were some earthquakes up in the injection unit. So this is the first thing we know, right? The earthquakes are primarily in the crystalline basement. We see relatively limited, if any, activation of the faults within the Ellenberger. Once you have a lot of stations in the ground, you start recording earthquakes in other places, but because we never put seismometers on top of any of these other source zones, we lose depth control. So you can make cross sections through those sequences, but usually it looks highly scattered because there's just not control on the depth. So in this area, because the earthquakes are always above 8 to 7 kilometers, we really focus on getting a station right on top of these earthquake sequences.
Heather, on your cross section, the faults kind of ended somewhere midway through in the strata and somewhere in the basement. So they are confined. I assume at the bottom you just don't know if they.
Yeah, in the bottom we just don't know.
And at the top, that means they're older in their geologic history than whatever they.
That's right. I'm going to show a slide with the top of the here in a second. So again, what we have seen in the Fort Worth Basin is that usually there's a series of mid-magnitude 3s rather than a traditional main shock aftershock, right? So you'll have a few 3s or maybe 10 3s located within the first month, and then the sequence continues. And this is just another way of looking at the SMU catalog, color-coded now by fault, versus the other catalogs. So USGS, the TA catalog, and then when TextNet goes into place. All right, I'm not going to talk about this, but we do match, we do template matching or matched filtering. We're moving into more machine learning to build out the catalog. But I really want to, and the reason we do this is not only to get better earthquake statistics and image the fault, but to try to understand when the sequences began. We haven't really been looking for repeating earthquakes, which I know is a common thing to do with these sorts of methods. But I'm going to kind of just blow past that for now. Again, we concentrate on trying to understand when the first earthquakes were, since our stations were not usually right on top by the time those earthquakes happened. All right. So of course, we locate the events. We were very interested in understanding in situ stress or regional stress. We calculate focal mechanisms. We usually have primarily upgoing rate paths. So we do, we use hash. So we have to use SP amplitudes in addition to first motions in order to get focal mechanisms. So these are not moment tensors. What we see is primarily northeast southwest trending normal faults. with maximum stress in the basement at about 20 to 25 east of north. It's actually the most interesting thing about some of these focal mechanisms is how similar they are. There's not actually a lot of focal mechanisms variability. In some sense, these earthquakes are really boring. I've had high school students pick these earthquakes. So these are just very clean local events, very similar focal mechanisms on these northwest, southeast trending normal faults. Dip is about 60 or so. All very much in agreement with SH max data from borehole breakout information that Stanford has collected. All right, so people were asking. So Beatrice Magnani, our exploration seismologist, did a very nice paper in 2017 on understanding the deformation history of these faults, looking at seismic reflection data. So this is this was the only 3D volume we were given access to at SMU. It's located along the Irving-Dallas fault. In fact, the Irving-Dallas fault is not in the 3D volume, it would be just off this volume, but this is what the seismic reflection data looks like. So this particular fault that generated earthquakes lies underneath the Ouachita thrust front. Here's the Barnett. This is the Ellenberger. You can see that these little faults displace the Barnett and the Ellenberger, but they don't really go into the overlying units. And you can barely see any sort of offset at the top of basement. So these are not huge. These are not huge faults. These two look the same. I'm not showing another example where we have like 3 faults, including one of the faults that are generating earthquakes, and all 3 look identical. And only one of the faults is generating earthquakes. So, we don't understand that. What we do know is that there is a pathway for hydraulic conductivity. And none of these faults have appreciably deformed materials younger than about 300 million years, right? So it looks very different than the New Madrid data set, which is the point of Beatrice's paper.
Does the seismicity is due to wastewater injection? So because of the connectivity of the faults, permeability, is there any, maybe the oil companies don't share it, but is there any stimulation of production due to the wastewater, in the vicinity of the faults, if they have wells?
So
so upward migration of the fluid might stimulate the well production.
So it goes back to that Viola-Simpson unit. So in the eastern part of the basin, no, because there's a unit that really separates the Barnett from the Ellenberger. Out in Azle, one of the reasons why we think there's earthquakes in the injection unit is because the Viola-Simpson doesn't exist there. And those production wells actually generate a lot more wastewater than the wells to the west or to the east where the Viola-Simpson exists. Basically, it looks like frac energy if the Viola-Simpson's not present, frac energy can break into the Ellenberger, which had its own natural brine in it. And when they produce the natural gas, they're pulling water out of the Ellenberger. So when you start to do the water balance, it becomes quite complex. And there's not a lot of data tracking the geochemistry to understand what was in the Barnett versus the Ellenberger versus what was the frac water. Okay. So that was lesson 1. Lesson 1B is that most of these northeast southwest trending faults hosting earthquakes are near critically stressed in the modern stress regime. So this actually comes out of Peter Henning's group at UT and the Mark Zobak's group at Stanford. I was involved because I provided the earthquake catalog, but they're doing fault slip potential. So if you know the dip of the faults and you know SH max, and you make some additional assumptions, including what your pore pressure increase is, You can actually do a calculation to understand what the fault slip potential is of the faults. And that's what this green color is representing. So the darker color means that the faults are oriented in such a way for higher slip potential. Some of these high slip potential faults have generated earthquakes, many have not. Some faults that generated earthquakes do not have high slip potential under these series of assumptions. So it's an interesting data set that has been published in other oil and gas basins, but even in the Fort Worth Basin, there's some questions on how you interpret it and what a sort of predictive tool it is. So as Richard pointed out much earlier, right, why do some, but not all of these faults slip? This is still a question we don't have an answer to. And the words on this slide, I think I essentially just stated, right? We have one fault in Northeast Johnson County where we had our magnitude 4 that once we did the template matching through the transportable array, we saw in fact that the fault had been active for 10 years. It's been active for 10 years. The largest earthquake just occurred well into the sequence. And then that's when we put the seismometers on top of it. So this remains a conundrum. All right. The first earthquakes in the Fort Worth Basin occurred near the highest injection wells or highest volume injection wells, kind of like you would expect. So when the transportable array came through and Cliff did his original work, right, the red is his catalog, and it was near these high volume injectors. What you're looking at here are two snapshots where the blue background color just represents cumulative wastewater injection into the Ellenberger over these time periods, 2008 to 2010 and 2014 to 2018. And you can see, the first earthquakes were kind of in these areas of dark blue. The one exception looks like this area here. Well, this is at the international airport. If you've ever flown into DFW, it can be a great or very negative experience. But if you look, there's actually shale gas wells. They drilled a shale gas well near what's called the airport fault. The fault throw was too big. They turned that shale gas well, which was never going to produce, into an injector. They put a lot of water down into it and they generated earthquakes right away. So it wasn't a large volume injector, but they were literally within a few hundred feet of the fault. So even this area here that looks like it's not in a very dark blue area was kind of an exception because they almost put the water directly onto the fault. Now, however, this is again up to 2018, the seismicity has spread considerably across the basin. And what I'm going to argue is that it's the cumulative history of injection that matters now. You can't see an earthquake and look at the nearest well and think that well triggered this earthquake, right? It's what has happened over these 10 or 15 years at this point that really matters. All right, so, over the last decade, the seismicity has migrated away from the high volume injection wells, but you have to understand that the pore pressure change and the poroelastic change is just going to continue to migrate away from all of the injectors, not just an individual injector. All right, so our lesson 2 is, unfortunately, we have also not found a clear and easily quantified predictive relationship between the earthquakes, the faults that do have earthquakes, and the injection wells. So these figures come from 2 papers out of UT. One is from Peter Hennings. This is just showing in blue the disposal information I'm talking about. So this is the disposal into the Ellenberger. There are actually other units that they dispose into. Again, it peaked in 2012. Seismicity kind of peaked in that 2015 time period. And then this just shows throw on the faults in the fault database versus length in meters. And so The ones highlighted in black are the faults that have had earthquakes. And then all of the other symbols are, faults in the database that haven't generated earthquakes, right? And you can see that there are faults that have higher throw and are longer that have not generated earthquakes. And there are lots of faults that are smaller with less throw, less length that have also not generated earthquakes, right? The seismogenic faults just kind of fall in the middle of this distribution.
They do look like they cluster though, right? I mean,
Yeah, they do cluster in this kind of, yeah, and then the colors are where the source information is. So I'm gonna go way long at this point. The pink circles come from a 3D seismic data set out on the western edge of the Fort Worth Basin. The companies provide the fault interpretation, and so that particular company's 3D seismic data set has hundreds more faults than any other company. So
when a fault gets activated, right, has seismicity on it, does the whole mapped fault tend to slip, or just small sections leaving behind more potential to continue the slip?
it depends on if you have mapped the fault from 2D seismic reflection data or for 3D seismic reflection data.
Right.
So, and that's because the 3D seismic data usually ends up with a fault map of anastomosing very small fault segments, where the 2D seismic reflection data ends up with, I've mapped it over here and I've mapped it over here, so let's just link it. And so it's an excellent question, but it's hard to know because there's only one of these active faults that have a really nice 3D seismic data set for it, and SMU has never been given permission to look at it. We have to rely, UT has, but we haven't. All right, now, an original question, which was naive, and we're gonna go fast, is how small of a stress change is necessary to induce the first earthquake? Well, we know from aftershock sequences that the answer is not much. And in fact, for induced earthquakes in the Fort Worth Basin, the answer appears to be not much. And so, you know, we know that Ellenberger is overpressured. There's one data set that had to be collected after the magnitude 4 that shows that the Ellenberger was overpressured from injection by 2015. So it's not gravity driven anymore. This is just from that magnitude 4. This was the template matching that I referred to earlier that shows that the magnitude 4 was actually well into the seismic sequence. And the template matching revealed that fault had actually been active since 2008. This is just the injection information from the 5 nearest wells. So we know it's above hydrostatic. And we know that if you just do pore pressure diffusion modeling with the monthly injection information that gets reported once a year, you get small values. So this is from the airport. This is work that Paulo Borri did. So this is where they injected almost directly onto a fault. And, you know, we modeled both in the basement and in the Ellenberger at 3 points, because this is one of our sequences that actually the earthquakes appear to migrate away from the well with time. But, you know, these pressure changes are not very big, right? 0.16 to 0.2 MPa. We've done pore pressure diffusion modeling out in Azle as well. This is work by Matt Hornbach and others. And, you know, these very small stress changes are what you would calculate even when you include production of water, not just injection of water. And again, you know, 0.4 MPa, right? But you get significant pressure differential across the fault when the injectors are on one side and the producers are on the other. So it can be a very interesting geomechanical system to study, but the pressures themselves, very small. So what's more interesting to me now is what type of stress change and what kind of slip is necessary to induce the first earthquake, because we've done the like nearest neighbor determination, for example. You know, once the sequence starts, there's a lot of earthquake triggering. So it's really a question of how did it start, right? Once it starts, it's kind of just going. But how did it start? Is there a seismic slip? This is a big question in induced earthquakes. If there is a seismic slip, how are you going to tell? And then what's the balance between seismic and aseismic slip? If there's in fact a seismic slip on these faults. So what we did is we turned our attention to fully coupled poroelastic and pressure diffusion modeling. The big question for us has always been, why did the Irving Dallas earthquakes occur? They're not near an injection well, they're underneath, that's where the risk is, right? This is the big driving question. You put a magnitude 4 out in the country, but why were there magnitude 3s under the city when there's no injection allowed in the city of Dallas, right? So you kind of get a hint at what's going on from this nice work done by Zhai and Sherazai in 2018. They misnamed the earthquake sequences, which kind of annoyed me, but you can see even back then, this is just cumulative, this log R, right? So here you have mu delta P, right? It looks very similar to the cumulative injection, essentially, while they're looking at poroelastic. Now, the thing is back then, they just assumed non-dipping layers, right? They just assumed a flat line basin and did a fairly quick calculation using the NEIC catalog for comparison. So we want to do better because we have a lot more information now, right? We have 3D geology, we have faults, we have a higher resolution earthquake catalog. So what Lewis did is he did fully coupled pore pressure diffusion and poroelastic modeling inside the console multiphysics software. This allowed him to include the full 3-dimensional dipping units. He then, you know, again, just to remind you, he put all the faults in. He had to assume a permeability for the Ellenberger in the basement, but there was some data to kind of constrain the permeabilities that he used, right? He had the earthquakes. It could all go into the model. Well, the earthquakes don't go into the model, but the injection data goes in as monthly injection data. So this is a movie. I think it's moving. And what you're looking at is pressure or stress change over time, right? So this is MPa. I have some other figures with the units properly noted. So you're seeing where the higher volume injectors are, right? And you're seeing stress change spread out over time. All right, so the modeling results end in January 2019, just based on when the reporting period was for the injection data and the fact that PhD students have to graduate. That was a joke. All right, so we assume in this model that the faults have a higher permeability. So provide pathways. We run models where the faults don't have a permeability difference with the Ellenberger or basement. And then we use different fault widths because we don't understand what a damaged zone looks like after 300 million years. So we do a lot of testing. I'm only showing one of those results. And again, we focus on understanding from an interpretation purpose, what is causing the earthquakes up here in Dallas, if it's a cumulative pressure effect. So we draw some cross sections through the model, starting from Northeast Johnson County up to Dallas. And so what you're looking at here is distance from Venus to Dallas Irving. The colors are color coded by time, and this is just the pore pressure change. So this is just the diffusion. And you can see, you don't, and this is in the Ellenberger, you don't get much change, right? From pore pressure diffusion alone. If you do the same thing for the solid stress, so the poroelastic component, what you see is that the Ellenberger with injection over time actually has a negative pressure change. And the pressure translates into the basement. And when you get to just under 4 kilometers in the Dallas Irving area, you do get a positive poroelastic stress, or a stress change associated with poroelasticity in the basement. So the earthquakes would be occurring in the basement from 4.5 all the way down off of this map. So you might assume from this that if we had captured the early earthquakes, they may have been triggered shallowly, and then maybe seismicity migrates down with time. This is not something that we can capture in the SMU catalog because we always miss the first earthquakes. And
in your modeling on the left, do you take into account just injection, or do you also take into account the fact that you also remove some fluid by extracting some?
so this is the weakness in this particular study. So in this particular study, we don't include production. And that's because, well, there's not actually very good data on water production. So it has even more uncertainty than any of the other input data sets that we put in here. Now, there are more detailed poroelastic studies out of the BEG at UT that do consider production, like out in the Azle area or specifically in the Venus area, but across the whole basin. This was a basin-wide model. We didn't put that in there.
And can you explain again why in Dallas Irving, the Ellenberger pressure goes down?
So it actually, the Ellenberger, this is again, just the poroelastic.
Right.
The diffusion would behave, the stress change from the diffusion would behave differently. They've been separated out in the calculation here. So it's actually across the Ellenberger that the injection leads to a reduction in stress from poroelasticity, not just in the Dallas area.
Right, it does it everywhere, right?
Yeah.
So you're injecting down in the Venus area,
Mhm.
but somehow in response to that, things are getting not sucked out, but
Yeah.
pressure drops elsewhere.
Yeah, and so the y-axis or the x-axis is different.
Right, it's
in
much,
the area
it's much smaller there.
so far from the injectors.
Yeah.
All right. Again, if you look at when earthquakes happened in the Irving, Dallas area, by the time the earthquakes happened in the Irving, Dallas area, stress had changed in the basement, not by a lot, but all of the models, not just ours, but there's just a pore pressure diffusion model that can do 3-dimensional permeability. That's this one here. Everybody models that by the time the earthquake started in Irving, Dallas, if you consider the cumulative wastewater injection, pressure would have changed, or stress would have changed on these faults at the seismogenic depths. All right, so, which is a nice result. The values are very small. Okay, so how do we improve these models? What is the relevant fault density? What's the permeability of these faults, right? What's the damage zone width? Like, how should you actually be, what width of faults should you actually be putting into these models? We assume all faults are the same in these models, and that just can't be true. If you did all of this, what would you learn that's different? Or could actually provide you any sort of predictive information to mitigate. And then we have some questions about compartmentalization. There's clearly more faults under the Ouachita thrust front, which I didn't talk about, but so there is a changing density of faults across the Fort Worth Basin. If you're releasing strain that is essentially left over, which it appears you were doing, how would you figure out how much energy remained on these faults to be released in an earthquake? And this is where I'm really sad that I have gotten so far behind in my talk, but we studied stress drops, Doug. We did. We studied stress drops using the GIT method and the EGF method. Most of the earthquakes in the Fort Worth Basin just have regular stress drops associated with intraplate earthquakes. There is one exception, and again, it's the airport where they inject it almost directly onto a fault. And in the airport situation, we see low stress drop. All right, so we use Brune source, not fairly standard stress drop calculations. So we get low stress drop. We only get low stress drop near the injection time period, really near the injection well. The more distant earthquakes don't have low stress drop. So it's just this one space and time set of earthquakes that have low stress drop. And, you know, we're writing a paper where we're going to ask the question, are these initial low stress drops because you're actually seeing the direct effect of the injection, or is this a measure of aseismic slip? So there's some laboratory experiments that have recently come out that would, and some Canadian data that have the suggestion that these lower stress drop events might have lower frequency, lower corner frequencies, and be indicative of some involvement of aseismic slip. An interesting idea. We can take all of the data and try to understand what the largest earthquake could be in the Fort Worth Basin. We've done that. Kind of comes out of the low magnitude 5, which is somewhat alarming for a built environment like Dallas, Fort Worth. But again, we've never seen a larger earthquake that takes up most of the available fault space and then has an aftershock sequence, right? We've only seen multiple events. And the largest earthquake we did record is a magnitude 4. What we're sure of is that it's the cumulative history of wastewater injection and fluid production, right? Because the fluid production part can be very important within the Ellenberger that is an issue, right? So it's the evolution of the stress in the subsurface that is the key driver to understand. And, you know, it speaks to the need to continue monitoring because you don't know if the whole system is still evolving. You don't know when the hazard is going to return to background. I mean, background is when there hadn't been an earthquake for hundreds of years, if not thousands of years. It's a different question. So what are the best mitigation strategies, right? There's a lot to be learned from the Oklahoma cases. You know, you can't just turn a well off, that's bad. You know, you can't just turn a wastewater injection well on, that's bad. We didn't show that in Fort Worth Basin, but they've shown that in Oklahoma well enough. You probably can extract that information out of the West Texas data set. When do you know things have returned, right? So don't read this, this is way too busy, but we have some conundrums, right? We have an incomplete earthquake catalog in the Fort Worth Basin. We don't have enough earthquakes to do great statistics with. We have all these space and time issues in our catalog. When other people use the catalog, I have to review the paper because it's just like, I want you to use my catalog, but it's super messy. You can't really do that with it. And there are just some things we're never going to be able to answer. with what we have in the Fort Worth Basin. This fundamental question, how do you look at seismic reflection data or an earthquake catalog and understand what faults will generate earthquakes and which ones won't? We can't do that. Oklahoma couldn't do that, right? This is a problem. Right, and then what data do you need? This is the real key, or this is something we worry about, right? What data do you need? In Texas, we only ever received monthly volumes for 12 months, once a year. And the most interesting wells always reported right after AGU, so. Always very annoying, right? We need daily injection volumes and pressures. Down these follow-up tests that tell you about overpressure were really valuable. We only had a few. I think the fluid production information is just as important as the fluid injection information, and we have even less control on that. And then the permeability, right? Properties of the fluids, the source rocks, but primarily the permeability. But you have to integrate it. The seismologists aren't going to fix the problem of West Texas earthquakes. The geologists aren't going to fix the problem of West Texas earthquakes. It has to be an integrated data set, and it has to be timely. In Texas, it's not timely. In Oklahoma may be timely, but no. And you have to continue monitoring. So in Texas, there has to be a will to continue TexNet operations, which, speaking to the choir, to you all, right? And how you maintain a seismic network in a state like Texas. They've gotten 4 two-year funding periods, but it's always a question of how are you going to keep that going? Anyway, it took a lot of people to work, and each paper is individually interesting. And I didn't even talk about some of my graduate students' papers, which is a real shame. But thank you for inviting me, and I'll answer questions.
So it seems to me like there's such a great opportunity here for a controlled experiment, right? These faults that that are generating earthquakes, some that are not. And I mean, there must have been discussions of this. I mean, the idea of going, it seems to me, I might get in trouble with some of my colleagues here, it might be much more exciting to go and drill one of these or 2 of these faults to understand what's the difference between the faults, rather than some of the bigger tectonic faults that have been the focus in the past, of course. And then also to explore, sort of pumping histories, and I mean, really do a controlled experiment over a number of years to understand how do you, and you do it in an unpopulated part of Texas, obviously, and to really understand, what are the controls.
Unpopulated enough.
I don't know what unpopulated enough means, but there must have been discussions about this. So,
yeah, so there was, and the Fort Worth Basin was deemed too populated, and also the Ellenberger is deeper by a couple of kilometers than the Arbuckle. So there was an IODP or a CDP, really, workshop up in Oklahoma to drill into one of the Oklahoma faults, but that project never went anywhere after the workshop. And it never involved drilling into a known fault that had not generated earthquakes. And then in West Texas, the rocks are even deeper, actually.
So how deep? Just give us a sense.
So I'd have to look at the cross section.
I mean, here it was what, 3 or 4 kilometers?
Yeah, so
right?
here the top of the basement is at 3 to 4 kilometers depth, right? Because it dips. Up in Oklahoma, it's at 1.2.
Oh, I see.
Right, and then out in West Texas, the Delaware Basin is really steeply dipping. And there's 2 layers of seismicity, and there's hydrofrac seismicity, and it's just kind of a mess out there. And the basement contact comes out of the Diablo Mountains and goes down to like 5 kilometers.
But it's clearly not a case of there not being enough wells.
Yeah, no. There's plenty of wells. These are just the injection wells. The production wells would just, there'd be almost no color that you could see.
And how deep would these be? How deep would these wells be?
So the injection wells go into the Ellenberger, so that would be from 2 to 3, or what did I say, 3 to 4, so 2 to 3 kilometers depth, and the Barnett is just a few hundred meters above that.
So, I mean, so to go and drill 2 holes for this purpose is not that big of a deal, in the sense that there's hundreds of these wells of a similar depth. Right?
Yes. So the problem is that the metropolitan area is essentially these 2 counties and this county. And while this Johnson County is where most of the earthquakes are, while it's considered less densely populated, it's like Gilroy, less densely populated, not West Texas, not populated.
Do any of these wells cross the fault though? I mean,
So that's what they did at the airport, is they
Yeah,
started
that's the
to
fault.
horizontally drill and realized they were crossing the fault. So they turned that into an injection well.
they must have run calipers down to look for aseismic deformation.
Yeah. So out in Azle, for example, it's actually a graben. In fact, some of the earthquakes in the Ellenberger are probably on a karst side, on the edge of a karst feature. Which is probably why they're the only earthquakes in the Ellenberger we see. So the production is inside the graben, and then the injection is on the outside of the graben, and then they are very careful to not cross the faults with the production wells. They don't have 3D seismic everywhere, but
Well, we should probably thank Heather again.
Thank you.